In this lecture, we are going to discuss the countable nature of partitions of unity, and also we are going to give an application of the partitions of unity theorem. More precisely, we are going to show that in a paracompact and Hausdorff manifold, there always exists a differentiable proper function. Let us point out that the family of functions provided by the partitions of unity theorem is countable. In other words, set of indices such that the function is non-vaniscent is a countable set. This is a consequence of our construction, but it can be proved directly. Indeed, if we consider the set Fj, which is the set of indexes such that, so the set of indexes, let's say I, okay, such that the support of theta I intersection Kj is different than the empty set, because we already know that our family of supports is locally finite. This implies that such a set is finite for every natural number. And what happens is that actually if E does not belong to the union of Fj from j equal 1 to infinity, we get that theta I is identically 0. Okay? And the union of the Fj's is a countable union of finite sets, so it is a countable set. So this actually proves the remark. An important point is that from now on, all our manifolds are going to be Hausdorff and paracompact. Indeed, there are going to be Hausdorff and second countable, because we need SAR theorem and we need partitions of unity. An application of the partitions of unity theorem is the next result. Consider an Hausdorff and paracompact CR manifold. Then there exists a proper CR function rho from M to the non-negative real numbers. And how is that? We can consider our construction. Okay, but let's remind ourselves that when we build partitions of unity, we consider an exhaustion of M by compact sets, right? And what we actually found is a sequence of non-negative functions, okay, that had several properties. Of course, one of them is that the family of supports is locally finite, and another one of them is that the sum of all of these functions is equal to 1. But for instance, one of the things that we proved is that the support of any of these functions is a compact set for every j greater or equal than 1. And we also proved that if we consider the set, okay, of functions such that their support intersects KL, this set over here is always finite. Those are the ingredients we have. Okay, so let's consider all these facts, and now we are going to construct the proper function. So the proper function rho is going to be the sum from j equal 1 to infinity of j times gamma j, right? That's going to be the function that we are going to consider. And in order to show that this function is proper, it suffices to consider sets of this form where m is actually a natural number. Okay, it suffices to show that the preimage of these closed intervals is actually a compact set, right? But something that it is interesting is that if we consider this preimage, it is contained in the set of points in which one of the first m gammas is positive, right? Because if we have that for a point, the first m gammas are positive, are 0, sorry, then the function applied to x is going to be the sum from j equal m plus 1 to infinity of j times gamma j of x. This is going to be greater or equal that m plus 1 times the sum from j equal to m plus 1 to infinity of gamma j of x. But since these first fm functions at x are 0, this is exactly m plus 1. So what we get is that if all the values of x by these functions, gamma 1, gamma 2, till gamma m are 0, then the value of our point is greater or equal than m plus 1. So the preimage of the closed interval 0m is contained in here, right? And now, sorry, what we get okay, let's write down such property, is that if it's contained in that union, it's contained in the union of the closures. But that says the support. So it is contained, but indeed this is equal to the support of gamma 1, union the support of gamma 2, till the support of gamma m. But all of these supports are actually compact. So the preimage of the closed interval 0m is a closed subset of a compact set, okay, and then it is compact. And this happens for every natural number. And so our CR function is indeed proper. In the last lectures, we introduced fundamental techniques in this course as star theorem or partitions of unity. In the next lecture, we are going to give an application of these results, namely the Whitney embedding theorem. Thank you for your attention.